Hi, how are you guys today? I think you may have seen me try to go live and it may have glitched out. It does appear that things are working again, but we will find out as people show up. How's your Monday? Are you guys excited for the last week of classes? Are you guys ready for classes to be? Everyone's ready for classes to end. That's like a silly question. So, what all do you guys have planned for this weekend? You guys can say howdy as you hop into the box. It looks like we have you guys coming in. They have, if you popped in and then it canceled pretty immediately, there was some technical difficulties this afternoon. How are you guys today? So it's our last class today. I hope you guys have had a great semester. I've had a pretty fun one myself. So if you have questions about the final or about anything else, you can go ahead and drop that right in that chat box and I'll answer that. While you guys are coming on in, hey, it's so good to see everyone today. I'm going to miss our Wednesday chats and hangouts. So you are probably wrapping up your Alex. Here's how it's going to go. You'll notice that every week you could get up to 10 points depending on how many objectives you finished. There is one more knowledge check, and then you need to get your pi to 100%, or I think there's like 140 objectives. It's going to throw you a party. The confetti will rain. It will say you have finished your pi and you're all done. By next Wednesday at 3, you need to have completed your pi. You need to do all of the objectives. So there's one last knowledge check this week, which hopefully you guys worked on your Alex last week's. But if you get to your Alex and you're like, how much more do I have to do? Or you realize I have a lot of Alex left to do. You can either wait until Monday night, so you'll have all day Tuesday to work on your Alex, or if you finish your objectives early, you can then go ahead and what was I thinking? Oh, you can finish your objectives early and then you can get into them after. So we have a couple of questions. Jenna asks, any overall tips for the final? How should we study? The final is going to be quite similar to all of your other exams. Some questions where you can, there was drawing on the last exam. You'll have to draw on this exam. There will be questions where it's like a math question, like what is the limiting reactants? In the past, it's been relatively equally weighted, exam 1, exam 2, exam 3, and then the final is the last chapter 10. I think in the announcement, I said it was between 10 and 20%. This week on Friday, I intend to give you more information about that. Give you a little bit more concrete. I want to say it's usually around 15% of the final is new material. And then the other 85% will be relatively evenly distributed between the three. Trying to think if there's any tips. I would recommend if there are topics on exams 1, 2, and 3 where you were like, yeah, I didn't know how to do that. So if limiting reactants were your nemesis, or titration, so there will be limiting reactants, there will be a titration, there will be a draw the molecules, there will be all of the others. Marlo asks, how many questions will be on the final? I don't know. So if the exams have been roughly in the low 20s, it's basically an exam and a half. So I would guess somewhere between 30 and 40 questions. Some of it depends on how it's structured. I will include that table at the top which I think most of you guys have said that you liked. The table at the top with the point values, so that you can kind of figure out which ones you want to spend more or less time on. Christopher asked, by when do we need to get Alex? Your Alex, there's 2 due dates coming up. On Monday, in 5 days or whatever, your chapter 10 objectives are due. Your pie, the total pie, I will pull those scores Wednesday at 3:30. Like, not today, obviously it's after 3. But next Wednesday, while you're taking the final, I will go ahead and pull all of your pie scores. If you are curious, like, are you finished? I've gotten a couple of emails or people have popped in office hours to say, like, I finished, right? Feel free to send me an email. I'm happy to hop into Alex and say, you have 5 more objectives or you have 3 more objectives, whatever. So the pie score, if you've reached the point in the semester where you're like, you know what? I don't have time for this. What % do I have right now? When you sign into Alex, that front page that has the circle pie in it, in the center is either a number or a percentage. If it's a number, you can click on it and it will convert to percentage. And that is what % of your pie you finished. So if today it says that you have 85%, you can choose not to do any more. You can then do that and it will basically give you, you'll get an 85 out of 100. 100 out of 100 is going to be better in that case. So other things you might be wondering, your final grades will be calculated in Canvas. So when I release the final scores, whatever letter grade you see at the bottom or at the end where it usually says like Dr. Malcolm, B+, Dr. Malcolm, A, like at the bottom of your grades page, that should correspond to exactly what you see in MyWings for your final grades. Checking for other comments to make sure I didn't miss anything. Other things I can tell you about the final. You are definitely going to have to draw. There will be a titration. There will be a limiting reactants. If you think about the mini exams and the regular exams, those are questions that I have written and I am writing the final. There are no multiple choice. It will be the same as everything else. There will be 5 bonus points for writing your name on every page of your, of your short answers. I've had a couple of students recently who have missed pages. And so if you write your numbers on your page, it will help me figure out if you've forgotten a page. Just in case you're like, oh no. So there's that. I am hoping to have everything graded pretty quickly after our final, but it usually takes me several days, so we'll figure that out. Any other questions that you guys have about the course, about the final? If you noticed in the announcement last week, I posted a link for a Google survey to ask questions. It's kind of like ISQs, but things I care about. Did you watch the videos? Did you come to the live session? What kind of videos do you wish there had been? Simple questions, feel free to fill that out. It will help me as I move forward in this course, thinking about how I want it to work in the fall when I teach Gen Chem 1 again. So it doesn't look like there are any other questions. Today we have 9 questions for the material. If you have any other questions, I'm happy to answer those. Someone did pop into office hours and ask, is there going to be a review session? The answer is, I don't think so. I'm not planning on holding a review session. The SI final review session is tomorrow at, I think it's from 12 to 2. Hopefully Mahi's in here and can pop in the chat box and say exactly when their final review session is. I think it is tomorrow from 12 to 2. In the announcement, there are a variety of other office hours coming forward. I am available later this week if you're like, I got a question. And the exam 3 key should be up no later than tomorrow afternoon, so that you can check your answers and study. If you have any other questions, you can drop them right in that comment box. If you don't, let's talk about gas loss. Oh, Mahi is here, and I was wrong. It is not 12 to 2. It is 11 to 2 tomorrow. So you should definitely go. She is going to suggest topics. She's going to give you any tips and tricks. She's going to maybe talk about chapter 10, mostly review. If there was anything that I said this will not be on the exams, that is also true for the final. Particularly, I think I said that the activity series, there's a video, you guys watched the video, but it wasn't on exam 2. It will not be on the final either. So that is true for any of the topics. So let's look at this first question here. So the first question is, a hurricane has a pressure of 947 millibar. What is the pressure in torr, and what is the pressure in atmosphere? So a couple of things. One, the conversion factors are on the, my gosh, I feel like my brain has gone on summer vacay, kind of like everyone else's. The equation sheet at the second to last. So you do not need to memorize the conversion between torr and atmosphere or anything else. I would recommend writing it on your study guide for the final. So our first question today. So we're going to take our 947 millibar. We're going to convert that to bar. There are 1,000 millibars in 1 bar. And there is 1.01325 bar in 760 torr. And that equals that there are 710 torr. So that's the first. This is just like a unit conversion. So all the way back in chapter 1, and really all of the other chapters where we've done unit conversions, it's just this process by which we change the units from one topic to another using conversion factors. So our second one is to convert it into atmospheres. So you can either convert 947 millibar or 710. I'm going to use the 710. You get pretty much the same answer. So 710 torr, where 760 torr is equal to 1 atmosphere. And this gives you 0.935 atmospheres. So these 3 pressures are the same quantity, or the same amount of pressure, just in different units. If you have any questions, you can go ahead and drop that right in the comment box. If you have no questions, you can write none, drop an emoji, or we'll just go with those 2. I was going to have something way funner to think about, but I don't. And Mahi said, it is a cumulative session, including the major topics, both old and new. And she strongly recommends that you go. I will strongly recommend that you go. So I would recommend that you go. I know in the past, students that have gone to SI have done significantly better in this course. I know students who started going after exam 2 and have brought their grade up some. So please check it out if you can. Christopher has asked, will the SI session be posted as a recording? And the answer is yes. I have no idea how you get to that, but you should. It's probably in the SI course on Canvas, so you can definitely check that out if you can't get to it. Mahi, how long will the recording be available? In case student, is it just one day? Will it be up until the exam? Ooh, Marlo seconds the thirds. Marlo also recommends that you go. She says that it's helped her out tremendously. I'm not seeing any questions on this question, so I will go ahead and put up number 2. So, I'm going to erase the board. All right, our next question. In my office, I have a 450 ml Lysol. Ooh, so there is a time delay. Not that you didn't already know that. The SI review session will be available until the end of the semester, as will all of our sessions here. They're on my YouTube channel. You can check them out there. So the 450 ml Lysol spray can contains 0.134 moles of Lysol. If the can is stored in my office at 26.1 degrees, what is the pressure inside the can? So in this case, this is going to use the ideal gas law. And the ideal gas law is a pretty exciting equation. We're going to use it all the time. So that equation is PV equals nRT, where we have the pressure, the volume, the number of moles, the ideal gas law constant, and the temperature. Now, the trick is to make sure that your R value matches all of the others, because you can put the pressure in different units and the volume. Temperature is always in Kelvin, and moles is always in moles. So in that case, you can use any R value you like. Those will also be on the equation sheet in that case. So one of the things a lot of students always ask is, so how do we best tackle these type of problems? I think chapter 5 and chapter 10 both are really interesting topics where a lot of times, maybe not interesting, sometimes students go, I don't know what to do or what equation to use. So I'm a big fan of reading the question and writing down, which I'm going to do right over here, all of the different variables. And then if I don't know what to do, I go look at my equation sheet and I say, oh, that one uses all the variables. So in this case, it asks, what is the pressure? So P is our question mark. And then the volume, so it's a 450 ml Lysol can, but we need that to be in liters. So that's 0.450 liters. The number of moles is 0.134 moles. And the temperature is 26.1 degrees Celsius. But temperature needs to go into Kelvin. So, like we're going to do a lot today, we're going to add 273.15 Kelvin, or to get us to Kelvin, and that's 299.25 Kelvin. So now with this information, we're going to go back to our equation. So the pressure is equal to nRT over V. So now we're going to just plug in all of these values we got over here into this equation. So we're going to take our 0.134 moles. We're going to multiply that by an R value. I'm a big fan of this one, 0.08206 liters, atmospheres, mole, Kelvin. Then we're going to add in the temperature of 299. .25 Kelvin. We're going to divide that by the volume, which is 0.450 liters. And when we plug this into our calculator, we get 7.312 atmospheres, which based on our sig figs, so in the problem, sig figs are back, the least digits is 3, which we see that in several values. And so from here, that's going to give us 7.31 atmospheres. What questions do you guys have about this material or about this question? And I will scoot out of the way so that you can look at the answer. If you don't have any questions, you can go ahead and write none right in that comment box. I will give you guys a little time to catch up. Not seeing any questions yet. I'll give you guys about another 15 seconds. If you've got any questions about PV equals nRT, I highly suspect that much of the material this week is a review. Ooh, we have some questions. How many sig figs does 0 degrees Celsius have? Because 273.15 Kelvin and 0 degrees Celsius have a different number of sig figs. So D to the first D, and I think he also said, this question came up in SI. So, two things. I see your question might be about this calculation here. So this value has 3 sig figs, but just 1 decimal place, right? So the 273.15 is the unit conversion between Celsius and Kelvin. So any Celsius temperature, add 273.15. And that gets you to 299.25. If this were to be the final answer that you were looking for, you would have to round to 299.3. Like if it was an addition and we were looking at sig figs, that would look there. When we think about 0 degrees Celsius as part of a conversion, so if you're converting from 0 degrees or somehow using the 0 degrees, if 0 degrees Celsius is a standard, then it has infinite sig figs. Kind of like how the atomic mass doesn't control how many sig figs you have in your problem. The other thing I will point out is sometimes with Alex or me or someone else, the temperature will be provided, but it's not used in the problem, and so the sig figs in there don't, I don't want to say don't count, but they're not necessarily part of that. So Christopher asked about the 273, which we asked about. And D to the first D, does that answer your question? As with all of the previous assignments, it is not my goal to trick you on sig figs. I try to make it to where they're relatively simple. For the temperature, it does get a little weird because this value has 3, but once you add it, it would have up to 4, and I showed 5. And so in here, the temperature won't control the number of sig figs. It would be the number of moles. So anything with more than that can't control that. Those are great questions. Any other questions? While you're thinking of them, I'm going to go ahead and pop number 3 up. Nope. I'm going to erase this. If we need to, we can not really rewind, but we can try. D to the first D, I am glad that you were honest, that it's a little weird, but there's some logic in there. Sometimes sig figs feel a little kind of wonky, but I think overall the point is to help us think about what is an important value. So our next question is also going to use PV equals nRT, so I went ahead and left it up there. A reaction occurs in a sealed vessel, which basically means a balloon, with a volume of 10.2 liters, a large one, at 64.1 degrees Celsius, and 8.12 grams of NO is produced. Calculate the pressure of NO in the vessel after the reaction occurs. So in this case, we're going to start pulling from some of the things that we might have learned in other chapters. So PV equals nRT requires us to have the number of moles. And on the final, I am for sure going to ask you how to convert grams to moles or moles to grams. So let's practice. So we know that we're going to use PV equals nRT. The first thing we're going to do is convert our 8.12 grams of NO using its molar mass of 30.01 grams in 1 mole of NO. And that gives us 0.271 moles of NO, which is N. So N equals 0.271 moles. The volume is 10.2 liters, and the temperature is 64.1 degrees Celsius, plus 273.15 Kelvin, and that's going to give us 337.25 Kelvin. Now, I do have to make a slight confession. Apparently, when I wrote these questions, I was very determined that we needed to solve for pressure. You will see on the exam, and both in Alex, sometimes it asks you to solve for the number of moles or the number of the volume or the temperature. I just happen to have always asked in these questions for pressure. That doesn't mean that the exam will not cover other entities. Sorry. So now we're going to solve for the pressure, which is nRT over V. Okay. So that's going to be 0.271 moles, 0.08206 liters, atmospheres, moles, Kelvin. And that's 337.25 Kelvin divided by our volume of 10.2 liters. And this is 0.735 atmospheres. So when we think about this PV equals nRT question, with a slight twist of having to convert grams to moles, what questions do we have about this one? If you don't have any, you can drop none in the comment box. I'll give you guys several seconds. Well, I will give myself seconds for you guys to ask questions in the chat box. I'm not seeing any questions. If you have one, feel free to drop it in that comment box. My guess is, again, these questions are a little bit more review. You've definitely seen this before, or hopefully you've seen it before. So now for something a little different. So in this question, we have an inflated balloon, like a hot air balloon or a weather balloon. And it has a volume of 6 liters at sea level, which is 1 atmosphere. This balloon ascends, it goes up, until the pressure is 0.45 atmospheres. The temperature changes from 22 degrees Celsius to minus 21 degrees Celsius. What is the volume in the balloon at this final altitude? So in this case, we're going to start to think about PV equals nRT in a different way. So in the videos, you'll notice that I proved why we can start to ignore the number of moles and there's no R value. So in order to use this equation, P1 V1 over T1 equals P2 V2 over T2, so we're going to use this question, P1 V1 T1 equals P2 V2 T2. So this works because it's a system. The same balloon is changing the volume, the pressure, and the temperature. But the number of moles needs to stay constant, so it is a system. So in this case, now my trick of writing down all of the different values out of the problem becomes a little bit more important. Before, there was only one pressure and one volume. This might remind you of M1 V1 equals M2 V2, but the question becomes, what is environment 1 and what is environment 2? And we need to make sure that we get those correct. So our P1 is 1.0 atmospheres. Our V1 is 6.0 liters. And our T1, it starts at 22 plus 273.15, and that gives us 295.15 Kelvin. So now we have P2, and that's 0.45 atmospheres. V2, that's what we want to know. And T2 is negative 21 plus 273.15, and that equals 252.15 Kelvin. So there are a couple of different ways you can solve this question. You need to isolate V2 by itself. So I will show you one way that you could rearrange these coefficients or the symbols in order to make it a little easier on yourself. So V2 equals P1 V1 T1 T2 over P2. So this is that we multiplied both sides by T2 to get rid of it over here and put it at the top, and we divided by P2 to get it here. Once you have this, you can then just plug in all of these values. So in this case, we have our 1.0 atmospheres, our 6.0 liters, our 252.15 Kelvin divided by 295.15 Kelvin, 0.45 atmospheres. And so V2, once you plug all of this in, is going to equal 11.39 liters, which is just 11 liters based on sig figs. So we've done a lot of math manipulation here. And you may have noticed that it takes me a long time to write out all these numbers because I'm including all of their units. That's probably my number one tip for how to be the most successful in any of the math equations that we have. If you write out all of your units, when you get to the end, the only thing left in this case, once you cancel, is the liters. I don't know why that's being weird. So in this case, that's what we see. We can get to this value. So I would make sure that you do that. So it also feels like you should be able, in this case, to leave it as Celsius, because you're going to cancel both of the temperatures out. It turns out that because in order to convert from Celsius to Kelvin, we have to add, you can't cancel addition in a fraction if it's on both sides. So x plus y and z plus y on the bottom, you can't cancel the plus y's. So in this case, we always have to convert to Kelvin in all of our questions. So are there any questions on number 4 that you guys have about how this calculation was done, what this calculation looks like, or how it works? And if you have none, you can drop that right in the comment box, and I'll know that you're ready for number 5. I will go ahead and put number 5 up in case you're ready to move on. It's just buried under everything else. So I'm not seeing any questions just yet. We'll give you guys another 5 or 10 seconds. If you've got one, you can go ahead and drop it right in that comment box. If not, that's okay too. So our next question is to calculate the density of SF4 at 25.1 degrees Celsius and at 1.12 atmospheres. So the density of a gas is a relatively simple calculation using the molar mass and PV equals nRT. So in order to do that, we are going to need to calculate the molar mass. So the equation for the density of a gas is D, which in this case means density, equals the pressure times the molecular weight over RT. Now, this is like a scripty fancy M. On the equation sheet, it's in like italics. So there are other values, and that could kind of look like a mu, but it is a script M in this case. So the problem tells us that the pressure is 1.012 atmospheres. The temperature is 25.1 degrees Celsius, so plus 273.15. And that's 298.25 Kelvin. So the question becomes, what is M? M is the molecular weight. And so for SF4, the molecular weight, as you probably remember, is just the total of all of the atomic weights. So that gives us 108.07 grams per mole. So that gives us everything, although it doesn't quite feel like it will be right. Well, let's find out. So we have our 1.012 atmospheres multiplied by 108.07 grams per mole. Now we're going to divide by R, which is the one I choose is 0.08206 liters, atmospheres, mole Kelvin. And the temperature in this case is 298.25 Kelvin. So now it's worth thinking about, and I'm going to drag you guys just a hair closer. Think about these units, because density is in grams per liter. And so when we cancel out our units, we get rid of our atmospheres, we get rid of our moles, and the Kelvin goes away. So we're going to be left with grams per liter. So when we plug this into our calculator, we get 4.47 grams per liter. So sometimes we treat density, now no one can see our question. Density is often, if we think about like a liquid, it's grams per mil. Gases tend to be grams per liter. But in this case, this is how you could calculate the density of any compound if you know the pressure and the temperature. So what questions do you guys have about this question? If you thought it was easy, you can write that in the chat. If you have no questions, you can write that in the chat. If you're still awake, you can say, I'm awake in the chat. Really, any movement in the chat sounds awesome. Thanks, Dee, to the first T. I just wanted to confirm. I mean, I am in this room alone with a bunch of chairs, but making sure you guys were following along. Thank you, thank you. I appreciate all of the confirmation that I am not teaching alone. So it doesn't look like anyone has any questions, even though we are, in fact, all awake, which is super exciting. So let's start to get into something that I would consider more interesting. So this type of question is going to start to, and I tried to bring examples in today, that are going to remind us of the things that we maybe have totally forgotten. Because balanced chemical equations, we didn't see a lot in the exam 3 material. That exam 3, really there wasn't many balanced equations at all. But we are definitely going to get that information. So Christopher in the chat asked, MW is the molar mass? Yes. So molar mass and molecular weight are not necessarily the same term, but they do give you the same value. So in this equation, we're going to start to use a balanced chemical equation again. What? Who's it? I mean, I'm pretty excited about this. So in this question, it says, pure hydrogen gas is produced when zinc solid interacts with sulfuric acid, H2SO4. What is the pressure of H2 produced when 21.34 grams of zinc is mixed with excess sulfuric acid at 34.1 degrees Celsius, and the gas is collected in a 312 ml balloon? So we are going to use PV equals nRT. And we're going to solve for the pressure. Not surprising. So the pressure, we don't know. The volume is 0.312 liters because it's a 312 ml balloon. So the temperature is 34.1 degrees Celsius plus 273.15, which is going to give us 307.25 Kelvin. so then it asks for N. And the thing is, it just gave us the amount of zinc. But in order for this to work, we would always be provided this equation, or whichever equation you needed, where the zinc solid interacts with H2SO4 to create H2 gas and zinc sulfate. So we know this, and we can use the stoichiometric coefficients to determine the amount of moles of hydrogen gas. So this is the moles of H2. So in order to do this, we're going to have to convert the mass of zinc to the moles of hydrogen. So we're going to take our 21.34 grams of zinc, using the molecular weight of zinc, which is 65.38 grams in 1 mole of zinc. And for every 1 mole of zinc, there's 1 mole of H2. And that gives us the N of H2 is 0.3264 moles of H2. So this part of the equation, we've learned this in chapters 2 and 3, where we can convert grams to mole. Just kidding, that's all chapter 3. And then we can use the stoichiometric coefficients, the big numbers up front, to convert from moles of one to moles of the other. I will tell you on the exam, it is more likely than not that these equations will not all have coefficients of 1. So in this case, you could have made the error to convert to grams of zinc and use that as your moles. On the exam, more than likely, I would ask something where you needed to convert using the stoichiometric coefficients. So now we can plug this into our calculator. Oops, first we'll write it out. So our 0.3264 multiplied by, moles, 0.08206 liters, atmospheres, mole, Kelvin, multiplied by the temperature of 307.25 Kelvin, divided by the volume, which is 0.312 liters. When you plug this into your calculator, we get, what do we get? 26.4 atmospheres. So this is just a different flavor of PV equals nRT. Pretty much it's PV equals nRT or a variation of PV equals nRT the whole time. So the last two questions that we have are going to be on partial pressures, which is the other thing that we can talk about. But even that's going to still use PV equals nRT, or some people like to call it other names like PivNert or something else. So what questions do we have about this question before we move on to number 7? We've got a none from D to the first D. Go. So, and we're not seeing much. I will bring that down a little bit further so you guys could definitely see it. So our next question, well, first I'm going to erase the board. Read first, then erase the board, then solve. So an Arctic weather balloon is filled with 20.4 liters of helium gas inside a prep shed. The temperature inside the shed is 15 degrees Celsius. The balloon is then taken outside where it's cooler. What is the volume inside the balloon at 6.2 degrees Celsius? Thanks to Quan for letting me know that you don't have any questions either. So in this question, it's again PV equals nRT-ish. So we're going to use V1 over T1 equals V2 over T2. So in this case, what we're going to start to see is, again, we just got to make sure that we match up the volume and the temperature from one environment with the volume and the temperature in the others. So in this case, we have V1, which is 20.4 liters. T1 is 15 degrees Celsius plus 273.15, which is going to give us 288.15 Kelvin. V2 is what we'd like to know, and T2 is 6.2 Celsius plus 273.15 Kelvin. And that gives us 279.35 Kelvin. So from here, we can then plug this into our equation. We're going to solve V2 equals V1 T2 over T1, which is 20.4 liters multiplied by 279.35 Kelvin divided by 288.15 Kelvin, and that gives us 19.8 liters, which is 20 with a bad decimal point liters using our sig figs. So in this question, well, I'll guess, what questions do you have about this example? And as always, if you have none, you can drop it right in that comment box. If you have one, let me know, and we'll answer it. So no one asked, but someone must be thinking, could we not have just left this as Celsius? You should go ahead and try that. And it turns out that you will get a vastly different answer, again, because the addition here is not the same as multiplication. So our next question is a mixture of 0.341 moles of argon, 0.382 moles of krypton, and 0.512 moles of xenon are contained within a 14.2 liter tank. If the total pressure within the tank is 980.1 torr, what is the partial pressure of each gas? So the next two questions are going to start to think about partial pressure. Partial pressure is going to start to talk about perhaps a more realistic environment where a gas cylinder or a balloon or something else contains more than one type. Most of the time, if you get helium balloons at your birthday, it's probably just helium. But if you fill up a balloon with air, it's going to contain CO2, maybe some oxygen, maybe some nitrogen, and whatever other environmental air you can acquire. So now we want to account for how much of the pressure is responsible, or is any one type responsible for. So to determine the partial pressure, we're going to use this equation, where P1 equals chi1 times P total, where P1 is the pressure and chi1 is the moles divided by the total moles. And so in this case, the first thing we want to do is to figure out what N total is. So N total is going to be equal to 0.341 plus 0.382 plus 0.512, and that's going to give us 1.235 moles. So we just added up all of the moles. Now you could imagine you might be giving grams on something else, but you just find the number of moles and add them up. So now we can determine the partial pressures for each of these. So the partial pressure for argon is 0.341 divided by 1.235, multiply 980.1 torr, and that is going to give us 271 torr. So we're going to do the same thing for krypton, and then we're going to do the same thing for xenon. For krypton, we're going to take our 0.382 divided by 1.235, multiply that by 980.1 torr, and that's going to give us 303 torr. For xenon, there are two ways that we could calculate the pressure of xenon. The first way is to use this calculation, which is 0.512 divided by 1.235 times 980.1, and that gives us 406 torr. Or you can do 980.1 minus 271 minus 303, and that should get you something really close or something that rounds to 406. So for the last one, you can always use subtraction in order to figure out the last partial pressure. So the next question is way more in-depth about partial pressures, but what questions do we have about partial pressures thus far? And if you have none, you can drop that right in that comment box, and I know that you're ready for question number 9. Go ahead and put it up in case you want to get started on it while we wait another 20 seconds here so that I can see your questions before we move on. Because I didn't realize the time delay was quite as long as it is. So, trying to give you time to see your comments so that I can answer them before we move to the next topic. So Mary asks, is it always going to be in torr? So in this case, on number 8, which I took down, but let me bring back up. So on number 8, it doesn't tell you to convert it to something else. So I would comfortably say leave it in what you have it in. You could have also converted this into atmospheres. You could have converted this into anything else that you wanted. But for partial pressures in this example, it started in torr and it can stay in torr. On the final, I will specify. Like, what is the partial pressure in this unit per the rest of that information? So you do not need to, unless otherwise indicated, change the units of the pressure to something else. That's a great question. What other questions do you guys have today? I'm going to go ahead and erase this while you guys think, and then we will work our last question of the day, number 9. So this question, whoops, let me make 8 go away. So in number 9, it says a 9.34 liter vessel contains 32.12 grams of propane, 16.12 grams of argon. If the tank is stored outside at 39.1 degrees Celsius, what is the partial pressure of each gas, the mole fraction of each gas, and the total pressure? So it's asking us for a lot of different things. So one, it's important to note, like, what are the things that we need to know? And how do we go about figuring that out? So I'm going to make us a little table that we're going to fill out. Yep. So for C3H8, it's going to ask us for N, chi, the pressure, and it's also going to ask that for argon. We also are going to need to know P total and N total. It doesn't ask for N total, but N total is going to be instrumental in the ability to determine chi, which is number of moles divided by the total moles. So the first thing we're going to do is I'm going to determine the number of moles. And this table is not going to be big enough. So the first thing we're going to do is, using the molar mass, convert our 32.12 grams of C3H8 divided by the molecular weight of 44.11 grams in 1 mole. That's going to give us 0.72817 moles. That's not going to be legible. 0.72817. So we're going to do the same thing for argon. So we started with 16.12 grams of argon divided by the molar mass, which is 39.95 grams in 1 mole. And that equals 0.4035 moles. 0.40352. So using this information, we can now determine N total, and that's going to be 1.13169 moles. So from here, we have a couple of different methods by which we can start to determine the rest of this information. You can, using the N value for both propane and argon, plug that into PV equals nRT. So PV equals N, that's not going to work. PV equals nRT. So you can either solve PV equals nRT twice, and then you will get both pressures, and then you can divide N divided by N total to give you chi. and then sum up the pressures. You can sum up the moles and solve for the pressure, the total pressure, and then use the mole fraction to calculate that. I'm going to choose to use the mole fraction. You can do it any way you'd like. You should get mostly the same answer anytime you work on this. So, P total is going to be equal to nRT over V, which is 1.13169 moles. .08206 liters, atmospheres, mole, Kelvin, multiplied by the temperature, which is 39.1 plus 273, which is 312.25 Kelvin. And I bet I'm off the screen. No, it's a miracle. Divided by 9.34 liters. So that gives us a total pressure of 3.10 atmospheres, which we can put in our table here. 3.10 atmospheres. So then we need to figure out for propane and argon what the mole fraction is and what the partial pressure is. And so in this case, the chi of propane is 0.72817 divided by 1.13169, which gives us 0.6434. That you're not going to be able to read. Hold. 0.6434. For the chi of argon, it is 0.40352, also divided by n total, 1.13169. And that gives us 0.3566. Now, your mole fractions should add up to 1, because it's 100% of the 2, so we can see that here. So now we're going to use the equation, and I'm sorry, it's a little messy. I should have, do this, give myself a little bit more board space. So now we're going to determine the P of propane, which is chi 1 times P total, which is going to be 0.6434 times 3.10 atmospheres, and that gives us 1.99 atmospheres. Is the pressure of propane. And again, for argon, even without doing a lot of math, we could figure out that it's 3.10 minus 1.99, or we can plug that in as the pressure of argon equals 0.3566 multiplied by 3.10 atmospheres, and that gives us 1.11 atmospheres as the pressure of argon. So we could fill out our table here. And we always want to confirm that when we add these two things together, they equal the total pressure. So I saw a question while I was working. So Anissa, trying to get out of the frame so that you can see me, but not, I will not cover up the work. So Anissa asks a question about Alex. Do we have to complete it to 100% in order for us to be graded, or will you grade just what we have finished until the end of the semester? So that's a great question. And your pie is whatever amount you accomplish. So if you decide not to finish your Alex, that's great. You will get credit for anything that you've done. If you're curious about how much you've gotten, feel free to send me an email. I'm happy to look it up for you and to give you some insights on that. But if you don't finish it, you can let it go. Or if you've realized that there's that one objective that just, you can't with it, you can totally let that go. There are office hours on Monday and on Tuesday. So if you're like, I just got to get those points, you can figure that out in that way as well. So it's whatever number of points or whatever percentage you've finished. So if you never open Alex again, you will earn points based on what you've done all semester. Great question. Any other questions? Any questions about this quite expansive question? I would expect something similar to this on the final. It is 5:45 or 5:44. If you have another class to pop into, it has been my pleasure to have you in this class this semester. I have had a fantastic time. I am very ready to meet many of you in person. If you are on campus in the fall, feel free to pop by my office and say hi. Although you may have to tell me your YouTube handle because I may not know your name since we may have never met. But it has been my pleasure. Feel free to reach out if you need anything else. And I'm happy to assist. If you've got to run, you can say bye in the chat, and we'll talk soon. So Anissa's follow-up question to Alex is, the percent that we finished in our pie is the percent that will be entered as your grade in Canvas. For the Alex pie, yes. So if that number is 79, I will enter 79 points out of 100 points. Keep in mind, if it is a value, not a percentage, then it may be over 100. So in that case, it will be converted to the percentage. But you can also pop into the grade book and look at it in there. Bye, Matt. Bye, Daquan. It's been my pleasure. Y'all have a fantastic rest of the semester. Y'all have a good afternoon. Enjoy the sunshine. It was sunshiny when I walked in the building. So if it's still nice outside, enjoy some time outside. And feel free to stop in office hours next week. Stay tuned for an announcement later this week with any information I have for the final exam. Anissa, that is my pleasure. Y'all have a fantastic day. I have had a great time, and you guys are wonderful. Have a good one. See you next semester, hopefully. Y'all have a great rest of your semester. See you around.